The news of NASA's near-light speed engine has taken the internet by storm. While its potential is captivating, many aviation enthusiasts are questioning its validity, if the engine truly defies the laws of physics as claimed. But the intrigue doesn't end there. What role does NASA play in developing this groundbreaking technology? And could it truly revolutionize space travel as we know it? Join us as we explore the details of NASA's newly designed near-light speed engine that might break the law of physics. Prior to the introduction of the speed engine, the M drive stirred up considerable debate in the realm of rocket science. Why? Because it seems to go against the fundamental laws of physics, the very things that make the universe tick. When British engineer Roger Scheuer first proposed the M drive, he described it as an engine that would use microwaves in a special cavity structure to create thrust, much like a light bulb, but with no moving parts and, crucially, no exhaust, no propellant, no problem. Physicist Stanislaw B. Shukalski, formerly with NASA's Glenn Research Center and now at UFIT in Fort Lauderdale, believed it couldn't possibly work. This skepticism stems from a core law of physics, the conservation of momentum. Simply put, for an object to move in one direction, it must push something in the opposite direction. Conventional rockets follow this by firing hot gases backward. The M drive, however, claims to generate thrust without any such action, no messy expulsion of gases. Despite this fundamental challenge, Scheuer's idea began to gain traction. In 2006, he claimed that his prototype could produce 0.1 Newton of thrust, enough to gradually move a small satellite through space. This breakthrough caught the attention of NASA's EagleWorks lab, led by physicist Harold White. Now, NASA engineers at the Marshall Flight Center in Alabama have taken things even further, developing a revolutionary engine that doesn't rely on any propellant whatsoever. Even more astounding, this engine has the potential to reach the speed of light, defying the very laws of physics that rocket science has adhered to for centuries. Before diving into the concept of this near-light speed engine, let's first explore the M drive and what it truly represents. In 2013, Dr. Harold White and his team conducted a test on an M drive prototype. They reported detecting an incredibly tiny thrust. To put that into perspective, it's roughly equivalent to the weight of a single eyelash. While this force was minuscule, it was far greater than physics would predict based on known principles. Naturally, this sparked excitement within NASA. However, despite their attempts to clarify that this was a preliminary test and far from conclusive, the media ran with the story, spreading the narrative far and wide. The buzz extended globally. In 2016, Chinese space agency scientists revealed that they had been testing a similar device for 6 years and hinted at plans to conduct space tests. However, the notion of generating thrust by simply bouncing microwaves inside a sealed chamber raised concerns among physicists, dating back to the M drive's original introduction in 2006. By the time China announced potential space trials, their claims were riddled with so many inconsistencies that they seemed almost comical. Still, they maintained a serious tone. Despite setbacks, hope persists. The U.S. Defense Advanced Research Projects Agency continues to fund research into related concepts, such as quantum inertia. While the M drive remains highly controversial, it has ignited interest in other futuristic propulsion technologies, some of which have transitioned from science fiction to reality. One such breakthrough is the ion engine. The fascination with ion propulsion began with science fiction. Philip Nolan introduced the concept in his 1982 novel, Armageddon 2419 AD, and franchises like Star Wars later popularized it. But how do ion engines work in real life? Unlike traditional rockets that rely on combustion, ion engines operate by accelerating charged particles. They typically use xenon gas, which is fed into a chamber filled with electrons. These electrons collide with the gas atoms, knocking away electrons and turning the gas into positively charged ions. The ions are then accelerated through an electric field and ejected from the engine at extremely high speeds, creating thrust. This process is akin to letting go of an inflated balloon, propelling it forward as air escapes. However, there's a challenge. The ejected ions carry a positive charge, and if left unbalanced, the spacecraft would accumulate a charge so strong it could no longer maintain the electric field. To solve this, a neutralizer sprays electrons into the ion exhaust, ensuring the spacecraft remains electrically neutral. Ion engines might sound like something from a sci-fi movie, but they've been powering real spacecraft since the 1960s. NASA's first big success with this technology came in 1964 with the SURT-1 mission. Since then, ion engines have advanced a lot, becoming a key tool for exploring space. What makes ion engines special? They're incredibly efficient, able to speed up ions nearly 10 times faster than traditional rockets. Some modern ion engines can increase a spacecraft's speed by 25 miles per second, a massive boost during a mission. However, they don't produce much thrust, generating only enough force to keep a piece of paper from floating away. That might sound weak, but once a spacecraft is in space, these engines shine, steadily pushing it to far-off destinations more efficiently than chemical rockets. Despite their slow acceleration, ion engines are perfect for long space missions. NASA's Dawn spacecraft, for instance, used ion engines to do something no other spacecraft had ever done: orbit 2 different asteroids. The European Space Agency's Bepi-Colombo mission is also using ion propulsion for its 7-year journey to Mercury. Even Elon Musk's SpaceX employs ion engines in its Starlink satellites for precise maneuvers in orbit. The roots of ion engines go back to 1917, when American physicist Robert Goddard explored new ideas for propulsion. Goddard is often called the father of modern rocketry, and while he didn't directly work on ion propulsion, his concepts inspired future researchers. The first working ion engine was built in 1959, and just a few years later, NASA tested it in space during the SURT-1 mission. For 31 minutes, the engine worked in the harsh environment of outer space, proving ions could propel a spacecraft. Around the same time, the Soviet Union developed its own ion engine called the plasma erosion engine. Soviet scientists continued refining their designs, eventually creating engines like the SPT-25, which became widely used on Soviet spacecraft by the 1980s. While the United States slowed its progress on ion engines in the 1970s due to budget cuts, interest revived in the 1990s as NASA planned ambitious deep space missions. One of the most famous missions using ion propulsion was NASA's Deep Space 1, launched in 1998. It was the first spacecraft to rely entirely on an ion engine, proving the technology's reliability for long-haul journeys. Other countries also joined the ion propulsion race. Japan's Hayabusa mission, launched in 2003, used ion engines to land on an asteroid, collect samples, and bring them back to Earth, a groundbreaking achievement. Ion engines have come a long way, transforming from experimental technology into the driving force behind some of humanity's most ambitious space missions. They work by providing gentle but constant thrust, enabling spacecraft to travel farther and faster than ever before. Whether it's reaching distant asteroids, orbiting dwarf planets, or powering satellites closer to Earth, ion engines are revolutionizing how we explore the universe. From their humble beginnings to their role in today's space missions, these engines are a testament to how patience and innovation can push the boundaries of what's possible. Ion engines have gone from experimental ideas to critical tools for space exploration, making some of the most ambitious missions possible. These engines are unique because they deliver constant, gentle thrust over long periods, enabling spacecraft to achieve incredible speeds and travel to far-off destinations. One of the first breakthroughs came in 1998 with NASA's Deep Space 1. This mission proved that ion propulsion could work reliably in deep space. The engine ran for an astounding 16,250 hours, far exceeding expectations and setting the stage for future projects. It was a major leap forward, showing the world what ion engines could do. The European Space Agency took the technology closer to home with the 2009 launch of the GO-C satellite. Using an ion engine, GO-C maintained an exceptionally low orbit, just 225 kilometers above Earth. This allowed it to make some of the most precise measurements of Earth's gravity ever recorded, proving ion engines weren't just for deep space. In 2003, ESA's Smart 1 spacecraft showed how ion engines could even be used for lunar missions. The probe spiraled out from Earth and successfully orbited the Moon, marking another milestone. Meanwhile, Japan's Hayabusa mission, which was also launched in 2003, relied on ion propulsion to visit the asteroid Itokawa, collect samples, and return them to Earth, a historic first. Hayabusa's engines ran for nearly 40,000 hours during its journey. NASA's Dawn mission in 2007 took ion propulsion to the next level. It became the first spacecraft to orbit two extraterrestrial objects, the asteroid Vesta and the dwarf planet Ceres. Over its mission, Dawn's ion engines changed its speed by an incredible 11 kilometers per second, a feat that would have been impossible with traditional chemical rockets. Ion propulsion isn't just for exploring distant worlds. It's shaping modern satellite technology too. SpaceX's Starlink satellites, designed to provide global internet, use ion thrusters to fine-tune their orbits and avoid collisions. This technology helps keep the satellites precisely positioned while extending their operational lifespans. But ion engines are only one piece of the puzzle in humanity's quest to explore space. Enter nuclear thermal propulsion, an idea first explored in the 1950s, but now seeing renewed interest. Unlike ion engines, NTP uses a nuclear reactor to heat hydrogen fuel to extreme temperatures. This creates powerful thrust, potentially making space travel twice as efficient as today's chemical rockets. With NTP, spacecraft could carry less fuel and more equipment or supplies. Missions to Mars could be completed in nearly half the time, reducing risks for astronauts. This technology could even open the door to exploring the outer planets and their moons, such as Europa or Enceladus. Countries like the US, Russia, and China are racing to make NTP a reality. NASA and DARPA's Draco program aims to test a nuclear engine in space by 2025, while Russia and China have their own ambitious plans. Safety and public perception remain challenges, but the potential rewards, faster, more efficient space travel, are too great to ignore. As humans push the boundaries of space exploration, ion engines and NTP represent two of the most exciting advancements. Whether it's precise satellite positioning, asteroid missions, or the dream of reaching Mars, these technologies are driving us closer to the stars. Let's move on to this near-light-speed engine that seemingly defies the laws of physics. Traveling at the speed of light might sound like something out of a sci-fi movie, but it's not as far-fetched as you might think. For perspective, light zips through space at a mind-blowing 299 million meters per second. That's incredibly fast, so fast that many believe it's beyond human reach. Yet history has shown us that the word impossible rarely stops us. NASA's latest invention might just be the next step in breaking barriers and exploring the unknown. Think back to 1947, breaking the sound barrier was once thought to be impossible too. Then came the Concorde, a jet so fast it cut the New York to London trip to under 3 hours by flying at twice the speed of sound. Though these jets aren't around anymore, they prove that once unimaginable feats can become reality. Similarly, the idea of traveling near the speed of light might seem crazy today, but history tells us not to bet against human ingenuity. Space travel, as it stands, faces a massive challenge: distance. Even the closest stars are so far away that it would take thousands or even millions of years to reach them with our current technology. Imagine trying to get to Alpha Centauri, the closest star system, using today's fastest spacecraft. NASA's New Horizons, which zoomed to Pluto at an astonishing 58,000 kilometers per hour, would still need 78,000 years to reach it. And that's not even considering the fuel it would need for such a journey. This is where NASA's new groundbreaking idea comes in. David Burns, a NASA engineer, has proposed a revolutionary new spacecraft engine that could potentially travel at 99% of the speed of light. What makes this concept even more astonishing is that it doesn't rely on traditional rocket fuel. Called the helical engine, this innovative design uses a clever method of acceleration that could change the future of space exploration forever. If Burns' engine becomes a reality, it could revolutionize how we think about space travel. Instead of taking lifetimes to explore distant stars, we could shrink those journeys to manageable timeframes, opening up the universe in ways we've only dreamed of. With this kind of technology, finding new planets, or even visiting them, might not just be science fiction anymore. It could be the next giant leap for humanity. Now, NASA engineer David Burns has proposed an even wilder idea: the helical engine, which might change how we think about space travel forever. So how does this futuristic engine work? It cleverly uses a strange feature of Einstein's theory of relativity. Instead of burning fuel and shooting exhaust out the back, it speeds up a loop of ions, tiny charged particles, until they're almost as fast as light. Here's where it gets interesting. As the ions move faster, their mass increases. This extra mass creates enough force to push the spacecraft forward without anything being expelled. It's almost like a physics magic trick. Imagine putting a spring-loaded ring inside a box. Normally, when the ring bounces around, the box barely moves. But if that ring were moving at near light speed, something incredible happens. Its mass grows, and when it hits the ends of the box, it pushes it forward. That's the basic idea behind Burns's engine. It takes advantage of this mass-changing effect to generate thrust in a completely new way. What makes the helical engine so exciting is that it doesn't need traditional fuel. Rockets today burn tons of propellant, which limits how far they can go. But Burns's engine uses an ion accelerator to create movement, meaning a spacecraft could, in theory, keep going indefinitely. This could open the door to exploring places like Alpha Centauri, the closest star system to Earth, at speeds we once thought were impossible. Of course, this idea is still in its early stages. While Burns's concept has sparked excitement in the scientific community, it's also drawn criticism. Some experts argue that the engine seems to defy known physics and might not work in the real world. Others compare the buzz around this concept to the hype surrounding the controversial EM drive, which many believe was too good to be true. Even so, Burns's helical engine is a fascinating glimpse into the future of space travel. If it turns out to be viable, it could revolutionize how humans explore the universe, making trips to distant stars faster and more practical. It's an exciting idea that pushes the boundaries of science and imagination. And who knows? It just might change everything. The helical engine, much like the EM drive, remains a concept that has yet to prove itself. Both ideas face a major challenge. They seem to break the law of conservation of momentum, which says that a system's momentum stays constant unless an external force acts on it. In simpler terms, if the helical engine could work, it would defy what we currently understand about physics. But here's the twist. It's based on Einstein's special relativity. This theory says that as objects move closer to the speed of light, they gain mass. Dr. Burns, the engine's creator, suggests a bold idea. Instead of a traditional design, the helical engine would use a coil-shaped accelerator to move ions in a loop. By speeding these ions up to nearly the speed of light and changing their velocity, the engine could theoretically create thrust without ejecting any fuel. Electric and magnetic fields would control everything, and it would operate in a vacuum without moving parts. It sounds like science fiction. However, there are big hurdles to overcome. For starters, the engine hasn't been tested, and many experts doubt it will ever work. If it does, it could challenge some of the most basic principles of physics, or perhaps expand our understanding of them. Even so, there are practical problems. The engine would need to be massive, around 200 meters long and 12 meters wide, to function. It would also require a staggering 165 megawatts of power to produce just a tiny amount of thrust, making it extremely inefficient. Another limitation is that the helical engine can only operate in the frictionless environment of space. Dr. Burns claims it could theoretically reach 99% of the speed of light if given enough time and power. This speed would let astronauts reach Mars in just 13 minutes, or the Moon in a little over a second. However, the current design remains purely theoretical, and we're far from seeing it in action. Despite these challenges, the idea is exciting. Unlike conventional rockets, the helical engine wouldn't need fuel, making it a game-changer for long-term satellite operations or deep space exploration. Even though it's just a concept for now, it opens doors to new possibilities and sparks hope for faster space travel. Will the helical engine take us closer to the dream of light-speed travel? Only time and innovation will tell. But with ideas like this pushing the boundaries of what we know, the future of space exploration seems brighter than ever.
Looking at history, new and superior aircraft have emerged approximately every 10 years. Now it's Dark Star's turn. The U.S.'s most lethal bomber fighter has proven itself in moments of service and is once again in service in Israel. But despite how powerful this bomber is, the U.S. military has developed an aircraft superior to all existing fighter jets. It is an upgrade-based version of its multiple well-reputed predecessors and was developed with artificial intelligence. Its weapon can destroy any target effortlessly and is practically invincible on any radar worldwide. With the recent upgrades in this active US bomber, how powerful is it really? What makes the Dark Star more lethal than any other fighter in the US arsenal? Join us as we delve into the US's most powerful combat fighter spotted in Israel. The purpose of building Dark Star was not to attack enemies, but to show what it could do and highlight the advancements in US technology. It follows the tradition of previous planes that once seemed unbelievable, like the SR-71 Blackbird, which amazed everyone with its high speed of 2,200 miles per hour. Later, there was the F-117 fighter jet with groundbreaking stealth capabilities. 6 years later, the B-2 bomber had an incredible variety of weapons and the ability to deliver them anywhere in the world. This next-generation bomber has recently been spotted in Israel. The B-2 Spirit was made to perform important missions for the USAF by flying deep into enemy territory to drop bombs, including nuclear ones. Unlike previous bombers, the B-2 is a flying wing with no separate fuselage or tail. It combines advanced technologies that are hard to detect and efficient in the air. Its low observable features let it operate at high altitudes, increasing range and sensor capabilities. The USAF claims its range is about 6,000 nautical miles. For armaments, the B-2 was initially designed for nuclear strikes, but it can also carry conventional precision weapons. It has bomb bays for internal storage, reducing radar visibility. The B-2 can carry up to 40,000 pounds of ordnance. It has been upgraded to carry modern precision munitions like JDAMs and has various conventional weapons in its arsenal. The B-2 has advanced avionics systems, including radar, navigation, and communication. The radar has a low probability of intercepting, and the avionics are continually monitored for safety. The B-2 uses fly-by-wire controls to maintain stability. The flight controls are designed to make the aircraft less visible to radar. The B-2's stealth features make it hard to detect by reducing its radar, infrared, visual, and acoustic signatures. It can perform undetected missions even in heavily defended areas. The aircraft's engines are hidden inside its wings, reducing their thermal signature. The B-2 is painted with anti-reflective paint to minimize visibility during daylight flights. Its radar cross-section is about 0.1 square meters. The B-2 uses various materials to reduce radar reflection and absorb radar beams. Most aircraft are made of a strong, lightweight composite material. Despite how lethal the B-2 bomber is, the U.S. military force still needed a whole aircraft carrier strike in the past, but now you can achieve it with just one airplane. Information about Dark Star started circulating in 2007, and its development was officially confirmed in 2013. The interest in it was so massive that it caused aviation and space technology servers to crash. This excitement is because Dark Star is positioned as the successor to the legendary SR-71, which set numerous world records in its time. The SR-71 was a groundbreaking plane known as the Blackbird, which was built to fly at speeds exceeding Mach 3 with a two-person crew in tandem cockpits. The pilot occupied the front cockpit, while the reconnaissance systems officer managed surveillance systems and equipment from the rear cockpit, overseeing navigation on the mission flight path. In an early attempt at stealth design, the SR-71 aimed to minimize its radar cross-section. The finished aircraft was painted in a dark blue, almost black, color to enhance internal heat emission and serve as camouflage against the night sky, earning it the nickname Blackbird. Despite carrying radar countermeasures for interception evasion, the SR-71's main defense was its combination of high altitude and extreme speed, making it nearly invulnerable. The aircraft's low radar cross-section and rapid speed provided a minimal window for an enemy surface-to-air missile site to detect and track it on radar. When a SAM site could lock onto the SR-71, it often became too late to launch a missile, and the SR-71 would be out of range before the missile could catch up. Even if a SAM was fired in time, the SR-71's sustained speeds and maneuvers made it challenging for the missile to intercept. The SR-71's titanium structure constituted 85% of its composition, with additional sections made from polymer composite materials. To withstand the high temperatures generated during flight, the inboard wings featured corrugated skin, expanding vertically and horizontally while increasing longitudinal strength. Fuselage panels were intentionally loosely fitted on the ground, aligning as the airframe heated up in flight. The aircraft leaked JP-7 fuel on the ground before takeoff due to the lack of a fuel sealing system to handle extreme airframe expansion. The cockpit's outer windscreen was crafted from quartz and fused ultrasonically to the titanium frame. Temperatures on the exterior of the windscreen reached 600 degrees Fahrenheit during missions, and cooling was achieved by cycling fuel behind the titanium surfaces. Landing presented additional challenges, with the canopy temperature exceeding 572 degrees Fahrenheit. Red lines on the wing's upper surface indicated no step areas, including the trailing edge and the thin, delicate skin where the inner wing blended into the fuselage, supported by widely spaced structural ribs. BF manufactures the SR-71's unique tires. Goodrich contained aluminium and was filled with nitrogen. Priced at $2,300 each, they typically required replacement after around 20 missions. Landing at speeds over 170 knots, the Blackbird deployed a drag parachute to reduce landing roll, brake wear, and tire wear. The SR-71 was designed to be stealthy, taking inspiration from the Lockheed A-12. It incorporated features to make it less visible to radar. The radar cross-section measured how much radar signal it reflected, about 110 square feet. Engineers used studies in radar stealth technology to shape the aircraft with flattened, tapering sides that would deflect radar signals away. They added chines and angled the vertical control surfaces inward. The aircraft's skin also had special materials to absorb radar waves. They even used cesium-based additives in the fuel to make the exhaust plumes less visible to radar, although they were still somewhat noticeable. However, the Soviet Union's radar technology improved faster than the stealth technology used against it. At the front of each inlet was a movable inlet cone called a spike, which played a crucial role in managing airflow. The spike locked forward on the ground and during subsonic flight moved inwards when the aircraft accelerated past Mach 1.6. This movement was directed by an analog air inlet computer, considering various factors like pitot static system, pitch, roll, yaw, and angle of attack. The spike's adjustment controlled the shock wave and airflow, minimizing spillage drag and optimizing efficiency as the air transitioned from supersonic to subsonic in the diffuser. During the early years of operation, analog computers sometimes struggled to keep up with rapidly changing flight environmental inputs. Issues like inlet unstart could occur, where the shock wave blew out of the front of the inlet, causing engine trouble and asymmetrical thrust. This led to violent yawing and other challenges for the aircraft and its crew. To address this, an electronic control system was later installed to detect unstart conditions and perform necessary resets without pilot intervention. NASA's research also revealed that vortices from the nose chines entered the engine, affecting efficiency. A computer-controlled engine bypass system was introduced to counter this issue, improving overall efficiency. The Pratt & Whitney J58 engines powered the SR-71, representing a significant innovation of its time. Capable of producing a static thrust of 32,500 pounds of force, these engines were most efficient around Mach 3.2, the typical cruising speed of the Blackbird. The engines used an afterburner that provided 26% of the thrust during takeoff, progressively increasing to 100% at approximately Mach 3. The air compression process, fuel addition, and exhaust flow through the afterburner affected the engine's performance. unique startup procedures were employed for the J-58 engines. Initially assisted by external combustion engines, the J-58 engines were equipped with a quieter pneumatic start system. The SR-71's use of unconventional fuels, such as triethylborane for ignition and JP7 for combustion, added to its distinctive characteristics. Regarding fuel, the SR-71 burned JP7, a challenging-to-ignite jet fuel. Triethylborane was injected for engine ignition, producing a distinctive green flame. Despite common misconceptions, the SR-71 did not refuel shortly after takeoff due to fuel leakage. Rather, it refueled mid-flight primarily because its maximum speeds were only achievable with aerial refueling. Aerial refueling was also essential for long-duration missions, as supersonic flights typically lasted at most 90 minutes before requiring refueling. The SR-71's astro-inertial navigation system, employing celestial observations for navigation, was a technological feat. The ANS used a star tracker to track various stars, continuously providing altitude and position data. This system enabled automatic navigation to preset destination points, controlled cameras and sensors, and contributed to the overall precision of the aircraft's flight. The SR-71 carried an array of sensors and payloads, including optical and infrared imagery systems, side-looking airborne radar, electronic intelligence gathering systems, and defensive systems for countering missiles and airborne threats. The aircraft's life support systems were designed to accommodate extreme high-altitude flight conditions, with crews using specialized pressurized suits and an emergency ejection system capable of handling Mach 3.2 ejections. Unfortunately, the SR-71, with its innovative design, advanced technologies, and unparalleled performance, was retired, and in July 2017, decades after the retirement of the Blackbird, the Dark Star prototype had its first flight test. It quickly proved itself by setting a new speed record of 4,550 meters per hour, equal to 6 times the speed of sound. No other plane had ever shown such high speeds. Just 5 years after the release of the movie Top Gun: Maverick, the Dark Star became known worldwide. In the movie, the main character flies this fighter jet. By the way, the plane's actual name is SR-72, but it got the nickname Dark Star from the movie. Some say that the US government used the movie to reveal the new fighter jet to the world without giving public information about it. The plane shown in the movie is just a concept. It's more about giving people an idea of what it might look like. The real fighter is different, especially in terms of weapons. Despite believing that the Dark Star has the LAWS system, Lockheed Martin confirmed that the plane has a much more powerful weapon. Since 2014, there have been tests on a combat laser, and its power has now doubled from 60 kilowatts. Lockheed Martin developed this system called layered laser defense. With changing environments and threats, we're exploring laser-directed energy weapons, particularly on ships. The system, LL, uses spectral matching of fiber lasers. Laser emitters send rays through an optical fiber into the alignment device. This technology cuts energy consumption by 50%, making it suitable for fighter jets like Dark Star. Dark Star can use the laser to take down missiles, projectiles, drones, enemy aircraft, helicopters, and ships. For instance, an A-120 ultra-high-speed missile can be destroyed in 5 seconds of beam exposure, and an aircraft engine can be taken out in about 3 seconds. We use the laser against targets we can't see visually, like in bad weather, smoke, or haze. Besides the laser, the SR-72 carries hypersonic missiles, cluster projectiles, and other lethal weapons. The full power of Dark Star's arsenal can be compared to Oppenheimer's testing nuclear bomb, allowing Dark Star to be armed with a nuclear bomb. The future of weapons may look very different. We're considering flexible payload bays with various missiles. The aircraft also has an invisibility mode. After a decade of testing, hyper-stealth biotechnology created an absorbent cover for Dark Star based on existing stealth technology. The creators had to make a special material to change radar waves' direction and speed to achieve the desired result. This makes a reflective cover, and radars won't detect anything. So Dark Star becomes invisible to the military, allowing it to get close to enemies and launch surprise attacks with its big range of weapons. It has a backup plan. If it's spotted by radar, it uses a system that scatters radar signals, creating a huge interference and making it impossible to figure out the fighter's exact location. The SR-72 is the most advanced aircraft in history, with unique features in every part. Its engine works at super high speeds, using special hydrogen fuel mixed with oxygen, boosting power and efficiency. The plane's body has a special shape and is made of unique materials, able to handle extreme temperatures above 752 degrees Fahrenheit, where the old Blackbird would fall apart. The fighter is controlled by both the pilot and artificial intelligence, which can take over complex tasks when the human pilot needs a break. Sure, there were cool planes before Dark Star, like the F-22 Raptor and F-35 Lightning II, but Dark Star outshines them in many ways. The F-35 has a top speed of 1180 meters per hour, and the F-22 is a bit faster at 1500 meters per hour, but Dark Star blows them away at 4,550 meters per hour. The F-35 uses too much gas and can only stay in the air for about an hour. Its maneuverability could be better. The size of planes matters because the bigger it is, the more weapons it can carry. The Lightning II is 52 feet long with a wingspan of 32 feet. The Raptor is a bit larger at 62 feet by 44 feet. Dark Star is even bigger at 72 feet by 52 feet and can carry much larger weapons. Its increased size allows it to have a laser system. Flying at the highest hypersonic speed, Dark Star can't be caught by enemy missiles. The AI on board can spot enemies in seconds and aim the laser system. We're exploring everything, from flight systems to battery technologies, using less hydraulics in the cockpit. Dark Star's power comes from the years of hard work by engineers who've tirelessly invented and installed new technologies, things we used to only see in movies. Each part of Dark Star is special and has unique features, making it better than the enemy. Engineers did their best to ensure the new fighter dominated the skies. Dark Star might have a weak opponent. The 6th generation NG-80 fighter jet is the closest. It has laser weapons, powerful bombs, and similar stealth technology, but it's also being developed in the US, so they probably won't face off against each other. NG-AD was born out of necessity, a realization that the enemy was becoming too powerful and threatening chaos worldwide. China had advanced supersonic aircraft with nuclear bombs, unmanned ships, and submarines, along with sinister satellites ready to disrupt coastal defenses and warning systems. In response, the United States, known for innovation and determination, created NG-AD. The fighter has a sleek design with advanced aerodynamics for top performance and stealth. Its impressive dimensions with a 45 feet wingspan and 68 feet length showcase its enormous capabilities, providing excellent lift and agility. The main weapons on the NG-AD are 6 radar-guided missiles carried under the plane. It's considered a top-notch fighter, especially because of its laser weapons developed by Lockheed Martin. These lasers have a powerful punch with an output of 350 kilowatts and can hit targets precisely within a range of 2 miles. In tests, these lasers have successfully destroyed enemy drones, missiles, and other aircraft. With changing environments and threats, laser-directed energy weapons are becoming more important and used on ships. The NG-AD is powered by the F-135 engine from Pratt & Whitney, which is revolutionary and surprisingly quiet. It produces 40,000 pounds of thrust, propelling the NG-AD to a top speed of Mach 9. This engineering achievement comes from careful research and advancements in propulsion technology. The engine's low noise emissions also contribute to the fighter's ability to remain stealthy. The NG-AD has an impressive range of 9,300 miles, allowing it to operate for long periods and protect the nation's interests. Besides its powerful laser weapons, the NGAD has a variety of conventional munitions in its arsenal. Its weapon bay can carry missiles, smart bombs, and precision-guided munitions. These weapons and the laser system help the NGAD maintain superiority in combat. Engineers are exploring various technologies, including flight systems and battery technologies, and using less hydraulics in the cockpit. Let's compare the NGAD with legendary planes like the SR-71 and F-22. The SR-71, famous for its speed of 3 times the speed of sound, can't match the incredible top speed of the NGAD. While the F-22 has impressive air-to-air missiles, the NGAD has an advantage with its laser weapons. The NGAD stands out for its advanced laser weaponry, pushing the limits of destructive power. Beyond its powerful weapons, the NGAD shows excellent coordination between its fighter jet abilities and cutting-edge laser weapons. Speed, maneuverability, and precision allow the NGAD to handle tough aerial situations easily. It's used for covert operations thanks to its sleek design, optimal performance, and smooth maneuvering at high speeds. The marvel of engineering lies in its efficient engine, crafted to minimize radar visibility. Advanced control units ensure precise handling and weapon control even during high-speed maneuvers. The NGAD, a technological marvel, moves through the skies, leaving amazement and destruction in its wake. The NGAD, on its way to becoming a legend, surpasses all expectations, making even the most legendary planes seem less impressive. It's not just about its incredible speed. Its design, control units, and every aspect make it a threat from land, air, and sea. No enemy aircraft, naval vessels, or ground installations can escape the power of this technological giant. The real strength of the NGAD is its capability to replace a whole army. That's correct. With unmatched speed, agility, and firepower, just one NGAD fighter can equalize the situation, removing the necessity for big military actions. It follows the idea that having quality matters more than having a lot, as its abilities go beyond what an entire army can achieve together. We can only anticipate further advancements in the Dark Star and NGAD's arsenal as we look to the future.
The U.S. aircraft carriers are finally becoming the most powerful vessels in the world. This country recently unveiled a game-changing weapon, an incredibly powerful laser carrier that is designed to take on the growing hypersonic missile threats with their unprecedented firepower and advanced technology. How is this new laser carrier better than the regular missile defense system? How effective are they against China's hypersonic missiles? Join us as we unveil the capabilities of the new powerful laser system that the United States recently unveiled. Aircraft carriers first proved their importance during the Second World War. When Japan attacked Pearl Harbor using planes launched from carriers on December 7, 1941, it showed how powerful these ships could be. After that, aircraft carriers became the most important warships. They were key in major sea battles in the Pacific, like the battles at Midway, the Coral Sea, and Leyte Gulf. These floating air bases have been the core of the U.S. Navy's offensive power for years. Today, they're bigger and more advanced than ever, but also more vulnerable to the growing number of America's enemies, especially China's Navy, the People's Liberation Army, Navy. As a result, many are questioning whether the massive cost of building and maintaining them is still justified. This situation gets even worse. The Chinese military has created targets shaped like an American aircraft carrier and other U.S. warships in the Taklamakan Desert based on satellite photos shared by Maxar with USNI News. The targets include a full-sized outline of a U.S. carrier and 2 Arleigh Burke-class destroyers built in central China's Ruqiang region. This area is near a place China used in 2013 to test its DF-21D anti-ship missiles, known as carrier killers. The new range suggests that China is still focused on developing weapons to target U.S. Navy ships, with this site being more advanced than Iran's similar target in the Persian Gulf. The carrier target appears to be a flat surface without key features like the island, aircraft lifts, or weapons, according to Maxar images. On radar, the carrier's outline is clearly visible, standing out from the desert like a target, as shown in images from Capella Space. There are two more carrier-shaped targets without metal, but their outlines still show they represent carriers. Other warship targets are more detailed, with many upright poles that could be used for instruments or radar reflectors to imitate the ship's structure. The facility also has a large rail system, and an image from October 9 showed a 75-meter-long target with advanced equipment on a 6-meter-wide rail. The area has been mainly used for ballistic missile testing, according to a review of Maxar images by All Source Analysis, a geospatial intelligence company that identified the site with satellite imagery. The mock-ups of likely U.S. warships, some on rails and movable, might be used to test target detection and tracking, though no signs of weapon impacts were seen nearby. The detailed setup, including sensors around the targets, suggests the area could be used for different purposes over time. Satellite images show the carrier target was first built between March and April 2019, rebuilt a few times, and mostly taken apart by December 2019. The site became active again in late September this year, with the structure nearly finished by early October. China has several anti-ship ballistic missile programs managed by the People's Liberation Army Rocket Force. The land-based DF-21D missile can hit targets over 800 nautical miles away and has a maneuverable warhead to strike ships. The larger DF-26 has a range of about 2,000 nautical miles. According to a Pentagon report, the Chinese military fired 6 DF-21D missiles into the South China Sea, north of the Spratly Islands, on July 2019. China is believed to be developing a longer-range anti-ship missile that appeared in 2016. The DF-26 can quickly switch between conventional and nuclear warheads and can carry out precise strikes on land or at sea in areas like the Western Pacific, Indian Ocean, and South China Sea. In 2020, China tested these missiles against a moving target in the South China Sea, but has not officially confirmed it. China is also developing a program to equip its Navy's H-6 bombers with a large anti-ship missile that was revealed in 2018. This missile, called the CHS-X-13, could be the largest air-launched missile and might carry a hypersonic warhead. Another platform for launching anti-ship missiles could be China's new Type 55 Renhai-class large destroyer, which the Pentagon report says will be able to carry such missiles. This isn't the first time China has built a carrier target in the desert. Since 2003, a large concrete pad the size of a carrier has been used as a target at the Shuangchengzi missile test range, regularly hit and repaired. The newer site in the Taklamakan Desert, 600 miles away, is more advanced, with ship targets that better resemble real vessels. There are still questions about which weapons will be tested at the new facility, but the advanced setup shows that the Chinese military is continuing to develop ways to reduce the effectiveness of U.S. naval forces near China, especially focusing on U.S. aircraft carriers. The Pentagon report from last week states that one of the main goals of China's rocket force is to keep U.S. carriers under threat from anti-ship ballistic missiles across the Western Pacific. To safeguard its extremely important warship, the USS Gerald R. Ford, the U.S. Navy is pulling out all the stops, arming it with the most powerful laser weapon ever developed. The USS Gerald R. Ford isn't just any ship. It is a nuclear-powered vessel that boasts of 2 nuclear reactors, each weighing over 1,000 tons. These reactors endow the ship with exceptional longevity, giving it the potential to power an entire city without interruption. Placed within its core are its 2 Bechtel A-1B nuclear reactors, which generates about 700 megawatts of power, equivalent to an astounding 952,000 horsepower, or nearly 2 million horsepower through its pair of colossal electric motors. Each motor is equivalent in size to 4 pickup trucks stacked together, generating power equivalent to 1.5 million horsepower. This floating vessel carries over 60 fighter jets, support, and tactical aircraft, with room for up to 90. Towering 25 stories above the water and weighing 97,000 tons, which is 32,000 tons heavier than the biggest battleships of World War II, it's a true behemoth. Amongst all the aircraft carriers in the world, the USS Gerald R. Ford claims the title of the largest aircraft carrier, enabling it to support various aircraft, helicopters, and UAVs, including the most sophisticated and advanced 5th-generation fighter jets. Mounted on this aircraft carrier is a Mark 15 Phalanx close-in weapon system, an unmistakable symbol of excellence within anti-aircraft artillery systems. Its illustrious reputation is well-earned, as it proudly boasts a remarkable rate of fire, capable of discharging an astounding 4,500 rounds per minute, and an initial projectile velocity reaching an impressive 3,600 feet per second. In inoffensive engagements, the Phalanx orchestrates a relentless ballet of projectiles, evoking the precision and swiftness of a laser-like performance. Notably, the USS Gerald R. Ford has a forward-looking weapon system, Lockheed Martin's Laws shipboard laser system. This state-of-the-art system draws formidable power from the aircraft carrier's nuclear reactor, enabling a sustained offensive against hostile aircraft and missiles at a substantial distance of 3 miles. The laser's devastating potency is sufficient to hinder aircraft electronics or obliterate projectiles approaching the USS Gerald R. Ford. Its massive 5-acre flight deck and cutting-edge technology are designed to keep it dominating the seas well into the 2050s and beyond. However, due to its immense size, the carrier is incapable of nimbly skimming across the water like a race car. The ship has almost 3 times more power than America's current supercarriers, producing about 300 megawatts of electricity, according to the Navy. Seeing it on the water is like watching a block of New York City moving at 34 miles per hour. However, new missiles from China, some of which can travel faster than 5 times the speed of sound, might make the USS Ford and the Navy's Pacific Fleet outdated. A serious report from Congress, which was updated in August 2022, has raised concerns about whether Navy ships can survive in combat against opponents like China, who have many drones and advanced missiles. Even though Russia also has hypersonic weapons, the Navy is more concerned about China. In the last decade, China has quickly grown its Navy and developed many anti-ship weapons, including missiles that can move faster than 10 times the speed of sound. China openly states these weapons are meant to stop American ships, and one of their test sites even has life-size models of U.S. aircraft carriers for practice. The USS Ford and similar ships have defenses against missiles, but these said defenses are not strong enough to fully protect them in a long fight against China's newest and quite advanced weapons. To stay in control of the Pacific and keep its ships safe, the Navy is investing heavily in a technology that has been hard to develop: lasers. Lasers have exciting benefits. Not only are they powered by large energy sources like the Ford's nuclear reactors, they can also fire at the speed of light, which makes them a good match for hypersonic weapons. They can also be reloaded quickly to fight off large numbers of drones, and since they don't need ammo, ships would have almost endless firepower. In 2021, the Biden administration created a Pentagon task force to assess the threat from China's fast-growing Navy. A year later, based on what the task force found, the Defense Department identified China as America's main strategic rival. China now has over 770 military vessels, more than double the U.S. fleet, and most of them are focused in the Pacific, while the United States splits its fleet between the Atlantic and Pacific. China's hypersonic weapons aren't the only danger. Carrier commanders have long known that large numbers of anti-ship cruise missiles are also a big threat. These missiles can overwhelm a ship's defenses, and swarms of cheap, long-range suicide drones could just as easily damage a carrier group. The Navy's problem is clear. Its largest carriers and most heavily armed destroyers aren't prepared to handle large numbers of airborne attackers. Right now, the USS Gerald R. Ford sails with a carrier strike group, a fleet of 10 or more cruisers, destroyers, and frigates, sometimes joined by a submarine or 2. At least 2 of these ships, usually Arleigh Burke-class guided missile destroyers, focus on air defense. They use powerful radars to detect threats more than 200 miles away and are equipped with surface-to-air missiles and Phalanx CIWs. The Phalanx system uses radar-guided 20mm 6-barrel Gatling guns that fire 4,500 rounds per minute, similar to the cannons on American fighter jets like the F-16. A carrier strike group has enough equipment to intercept dozens of missiles from up to 200 miles away. However, it becomes vulnerable once it runs out of interceptors, which need to be stored and replaced after a battle. Some supplies can be refilled at sea, but missiles cannot be refilled at sea. They have to be refueled at a port. The Pentagon calls this a depth of magazine issue, meaning enemies could take advantage by overwhelming the defenses with lots of attacks. The Pentagon believes the best way to defend against swarming drones is with lasers. Unlike the lasers in Star Wars, real laser beams don't explode on impact, but instead produce intense heat. At lower power, they can mess up a drone's sensors, and at a higher power, they can burn through it. Essentially, lasers turn energy into ammo. With nuclear reactors like those on the USS Ford, lasers could potentially fire thousands or even tens of thousands of times to stop incoming attacks. Because laser beams travel at the speed of light, they can follow and target fast-moving weapons, like China's hypersonic DFZF, better than traditional missiles. Gunners wouldn't need to predict where the target will be like they do now. Lasers are also much cheaper. The Congressional Research Service estimates that firing a high-powered laser costs between $1 and $10, much less than the millions it costs for defensive missiles. In 2014, the Navy installed the first laser on a ship for sea trials. Mounted forward on the deck of the amphibious transport ship USS Ponce, the 33-kilowatt SEQ-3 laser weapon system had a short, round, white-painted firing tube with two smaller tubes for sensors resting on its shoulders. To an untrained eye, it looked like an amateur astronomer's telescope. But even this early, low-power version delivered impressive firepower. A second, more powerful laser began testing in 2019. In August 2022, the Navy installed its first permanent laser on a destroyer, the Arleigh Burke-class Preble. The weapon, developed by Lockheed Martin, has a 60-kilowatt output and is integrated with the ship's advanced Aegis radar and weapons control system. The Navy calls it Helios, or high-energy laser with integrated optical dazzler and surveillance system. Later versions could be even more powerful. The Navy received its first high-energy laser system, called Helios, from Lockheed Martin in the third quarter of fiscal year 2022, and it is currently being installed on an Arleigh Burke-class destroyer that is getting upgrades, according to a company spokesperson. Rick Cordero, a vice president at Lockheed Martin, said that Helios improves the ship's ability to defend against future threats and provides extra protection for sailors. He emphasized that the system is designed to meet the Navy's specific needs and can be upgraded over time. Helios is part of the Navy's larger plan to increase its use of laser weapons. The Navy requested about $35 million for this group of systems in its 2023 budget, and the first system is expected to be used at sea that year. The weapon system helps fill gaps in defending against surface threats and surveillance, and can destroy drones and small attack boats. This technology is a big improvement over current systems, such as surface-to-air missiles and Gatling guns, which need ammunition and are expensive to use against cheap drones, according to an August report from the Congressional Research Service. Lockheed Martin thinks the weapon could eventually reach 150 kilowatts, but even at that level, it will be most useful against drones and small boats. To stop a wave of cruise missiles or a hypersonic weapon moving at speeds of Mach 5 or faster, the Navy will need a much more powerful laser. The Navy estimates that at least a 300 kilowatts laser is needed to defeat cruise missiles. This is because these missiles, besides being large and fast, have heat-resistant nose cones made from materials like pyrolytic graphite or ceramics, designed to handle the extreme heat of supersonic flight, which can go over 1,000 degrees Fahrenheit. Lasers will need to burn through these tough materials quickly. They also must be strong enough to overcome atmospheric interference and accurately hit a missile moving at 1 mile per second to destroy it. A new solution may be coming soon. The Navy plans to test a 300 kilowatts laser called HELCAP, or High Energy Laser Counter ASCM program, later this year. A 2020 photo behind Admiral Michael Gilday suggests that HELCAP will be based on the Navy's current Odin system, which is already on some destroyers. If the test is successful, HELCAP would be the Navy's first laser able to shoot down incoming anti-ship cruise missiles. However, even HELCAP won't be powerful enough to stop hypersonic missiles traveling up to Mach 10. These missiles can handle temperatures over 1,700 degrees Fahrenheit. The Pentagon estimates it might take a 1 megawatt laser, over 3 times stronger than HELCAP, to take them down. Luckily, megawatt-class lasers could be coming soon. The Navy gave Northrop Grumman a contract to develop such a laser, and in July 2022, the company finished a design for a high-energy laser that combines several beams into one. Northrop will first build a 300-kilowatt prototype, but the technology could eventually reach 1 megawatt. For the Pentagon, this technology is urgently needed, as billions are invested in aircraft carriers. With China's anti-ship weapons getting better fast, ships like the Ford are more vulnerable than they've been in decades. The future of the U.S. Navy might depend on stopping a single hypersonic missile, but the Navy hopes its new laser systems will be able to destroy these missiles at a much lower cost. The United Kingdom is also working on a laser system known as the Dragonfire. It was first shown to the public in 2007 at the Defence and Security Equipment International Conference in London. It is being developed by UK Dragonfire, a group made up of MBDA UK, Leonardo UK, Kinetic, and the Defence Science and Technology Laboratory. A production version is expected to be used on Royal Navy ships by 2027. Dragonfire uses advanced technology developed in the UK to create a powerful laser beam with better performance, faster reaction times, and longer range. It uses many glass fibers, but the full details are secret. The laser system includes a camera and a weaker laser for tracking, all mounted on a rotating platform. The laser has about 50 kilowatts power and is meant to protect land and sea targets from missiles and mortar attacks. It might be powered by a new flywheel energy storage system being developed by the UK and the US. The exact range of the laser is classified, but each shot costs just €50. The UK plans to use these high-energy lasers on future Navy ships, Army vehicles, and Air Force fighter jets, including the BAE Systems Tempest, and will test them on a Type 23 frigate and a Wolfhound vehicle. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.